Welcome. My name is Jakub Beranek and I'm going to present our paper titled Runtime versus Scheduler Analyzing Dask's Overhead. The goal of our work was to examine the bottlenecks and performance characteristics of Dask, a popular distributed task framework. We wanted to find out if it's better to improve its scheduling algorithm or to reduce its runtime overhead in order to improve the performance of executing Dask workflows. Our contributions include a detailed quantification of the overhead of Dask, where amongst other things, we show that for some workloads, having a clever scheduler is not that useful if its runtime efficiency is low. We also present RSDS, an open source Dask server alternative that provides better scaling than the Dask server in common workflows, has a swappable scheduler that facilitates experiments with scheduling algorithms, and it is also backwards compatible with existing Dask programs. Dask is a Python library that allows you to describe a computation in Python. It can then transform this computation into a directed acyclic task graph and execute this task graph either on a single machine or on a distributed cluster. In our work, we focus purely on the distributed cluster use case. To give you an example of how the Dask API looks like, here we create a simple MapReduce-like program using the delayed API. It is a low-level API that allows you to build a task graph directly from Python functions. Here we see the corresponding task graph for the code on the left. Each task corresponds to an individual Python function in the invocation. At the top, there are 3 mapping tasks that produce a number, and this number is then used as an input to the merge function. The edges in the graph represent dependencies, so the merge function cannot run until all of the previous tasks are finished. Please keep this merge task graph in mind, as we will examine it in several benchmarks later. In addition to this low-level API, Dask also offers higher-level APIs that mirror popular Python libraries, such as NumPy or pandas. Here we perform several queries on a data frame using a pandas-like API, and Dask can again transform this code to a task graph and execute it on a distributed cluster. The architecture of Dask consists of 3 parts. The client transforms the user's code into a task graph and then sends it to the server, a centralized component that schedules tasks to workers. The workers then compute the tasks, communicate amongst themselves to transfer data, and return the final results through the server to the client. Oftentimes, the client runs on a personal computer, while the server and the workers are deployed on a cluster, either in the cloud or on HPC. In our work, we focus mainly on the performance of the server, as it is often the bottleneck of the whole cluster. An important part of the server is its scheduling algorithm, which decides how to assign tasks to workers. Dask uses a Workstealing scheduler that assigns tasks to workers eagerly. If it finds a situation where some worker is overloaded, while some other worker is starving, it retracts tasks from the overloaded worker and then reschedules them onto the starving worker. The scheduler is quite complex, as it has been extensively hand-tuned over the last several years to provide good performance for various diverse use cases. We had some internal use cases where we noticed that Dask didn't scale as much as we would like to on HPC infrastructure, so we wanted to find out what are the main factors that limit its scaling. The first natural factor is the number of tasks per second. The Dask server introduces some overhead per each task. The Dask documentation states that this overhead is about 1 millisecond. So if the executed tasks are too short, distributing them with Dask will probably not provide large speedup. The second limiting factor is the number of workers, because they put a lot of pressure on the Workstealing scheduler and also on the central server. To see the effect of these 2 factors in practice, we prepared a benchmark that runs the simple merge workflow that was shown earlier with 20,000 tasks. We have executed this benchmark on nodes with 24 cores, and we have used 1 worker per each core. We run the benchmark in 3 configurations, differing by the duration of each task. On the x-axis, we scale the number of workers, and on the y-axis you can see the time to execute the workflow. We can see that if the tasks last 1 second, Dask scales up to about 1,500 workers. If we reduce the duration to 100 milliseconds, Dask scales only up to about 300 workers, and then it gets slightly slower with more added workers. If we reduce the task duration further, Dask scales only up to about 200 workers, and then it quickly gets slower and slower with each added worker, which is far from ideal. But why have we used so many workers per node? A natural way would be to run a single worker process per node, which would have a computing thread per each core. On the bottom side here, we show how this configuration ranks up on a pandas Dataframe workflow. The problem with this is that Python doesn't allow running more than one thread in parallel because it has a global interpreter lock, or also called GIL. Therefore, if you have compute-bound tasks written in Python, you cannot utilize multiple cores with this configuration. A natural way to improve this situation is to create a single worker process per each core. And indeed, we can see that it improves the performance. If the Dask server had zero overhead, this would be the ideal case. However, it turns out that creating so many workers alleviates the GIL problem, but it creates a new bottleneck. With so many workers, the Dask server starts to introduce a lot of overhead. So in reality, you might have to manually balance the number of worker processes per node to achieve the best performance. And this is not an ideal situation. While we cannot do anything about the GIL, we thought that it should be possible to reduce the overhead present in Dask. To see how large is the scheduler overhead, we have tried to plug in a simple scheduler into Dask. We found out that it is actually quite difficult to change the scheduling algorithm in Dask because the whole workstealing concept is ingrained very firmly into it. We have therefore decided to try to plug in a completely random scheduler. Its performance does not depend on the number of workers, and it should have much lower computational overhead than workstealing. But we also expect that it will perform much worse, because the built-in Dask scheduler has been extensively hand-tuned for a long time. We have performed a series of benchmarks on various workflows that we'll describe in more detail later. On the y-axis is the speed up of Dask with a random scheduler versus Dask with the built-in workstealing scheduler. On a single node with 24 workers, we can see that in some cases the random scheduler provides almost equivalent performance to workstealing. Sometimes it even surpasses it. If we add more workers, the gaps between the two schedulers get even smaller. This was surprising to us because the task assignments of the random scheduler were surely worse than the workstealing assignments. So it seems that the real problem lies in the runtime overhead of the scheduler and of the server. As I already said, we couldn't easily test other schedulers in Dask, and we found that reducing the overhead of the Dask server significantly is difficult, as it is written in Python. Therefore, we have decided to create RSDS, which aims to be a flexible and efficient drop-in replacement for the Dask server. To achieve this goal, we needed to improve scheduler flexibility to facilitate experimenting with different schedulers, and we needed to reduce the runtime overhead. Also, to make RSDS practical, we also needed to make it backwards compatible with Dask. Here is the architecture of a Dask cluster that uses RSDS. We actually use the original Dask implementations of the client and the workers, but the server part is replaced by RSDS, which is divided into two parts. The reactor handles low-level data processing, network communication and bookkeeping, while the scheduler focuses purely on scheduling tasks to workers. Thanks to this strict separation, the scheduler can be trivially swapped with a different implementation. It can also run in a different thread, process, or it can be even written in a completely different language. To reduce the overhead of the server, we have implemented it in Rust, which has a minimal runtime and no garbage collector. RSDS tries to minimize memory allocations because Dask is quite liberal with them, which contributes to its high runtime overhead. We also store key data structures in both the reactor and the scheduler in a cache-friendly way. We have chosen Rust because its safety properties make it easy to write correct and safe distributed applications. For scheduling, we have implemented a classical by-the-book workstealing algorithm that is much simpler and less tuned than the Dask workstealing scheduler. To keep compatibility with Dask, we have reused its communication protocol. Therefore, RSDS works out of the box with unmodified Dask programs, and even though it is not feature complete, it supports a large variety of common Dask workflows, as we will see in a while. We had to make a slight low-level protocol change in Dask. Dask sends messages represented by dictionaries. The dictionaries are arbitrarily split before transmission into several binary frames encoded with message pack, and then they are merged back when they are received. It is quite difficult to implement this arbitrary splitting of data structures in a statically typed language. Therefore, we use a simple encoding that keeps the original dictionary structure. This might seem like a trivial difference, but in our opinion, it is a crucial change that enables to implement the protocol practically in languages like Rust or C++. Our modification changes about 100 lines of low-level code inside the Dask core, and it does not require any modifications to users' Dask programs. To evaluate the performance of RSDS versus the Dask server, we have collected a series of benchmarks from the Dask examples repository. We use simple aggregations like merge or tree reduction. Those serve as scheduler stress tests, as they have a large number of small tasks, which put a lot of pressure onto the central server. We also benchmark various workflows that process data frames and n-dimensional arrays, and in addition, we also benchmark a real-world text processing pipeline. RSDS can run all of these benchmarks without requiring any modifications, which demonstrates that it supports the most common Dask workflows. The size of the benchmarked workflows ranges from several hundred to several hundred thousands of tasks. We ran the evaluations on the Solomon supercomputer with 24 cores per node, and we have used a single worker per each core, since the tasks were compute-bound. We have used from 1 to 63 nodes. We measure the time from submitting the DAG from the client to the server up until the completion of the whole workflow. Each benchmark was measured 5 times. First, we show the speedup of RSDS with a Workstealing scheduler over Dask with a Workstealing scheduler. On one node, we can see that the performance of Dask and RSDS is mostly equal, except for the stress test, where RSDS is up to twice faster than Dask. If we increase the number of workers and the number of nodes to 7, RSDS is faster than Dask in most of our workflows. This serves as an evidence that RSDS handles higher worker counts better than Dask's. To verify that this speedup comes from better runtime efficiency and not by a better scheduling algorithm, we also benchmark the speedup of RSDS with a random scheduler over Dask with a Workstealing scheduler. We see that for the stress test workflows, RSDS is still twice faster than Dask. And if we increase the number of workers, we see that RSDS is faster than Dask in many cases, even though it uses a completely random scheduler. To further quantify the exact overhead difference between RSDS and Dask, we have created a special implementation of the Dask worker that we call zero worker. The zero worker immediately finishes any task that arrives to it. With this zero worker, we can simulate infinitely short tasks, which allows us to measure the pure overhead of sending a task through the Dask cluster. On this chart, we show the average overhead per task, which is calculated as the duration to execute the workflow divided by the number of tasks. Please note that since with the zero worker the tasks are not actually executed, the only difference between these workflows is their task graph shape and size. We see that the average overhead per task for both Dask and RSDS is about 1 millisecond or lower. However, the overhead of RSDS is consistently smaller than the overhead of Dask. Here we examine how the overhead changes when we increase the number of tasks using the simple merge workflow. We can see that the overhead of the random scheduler in Dask does not change when task count is increased, and that it is generally lower than the overhead of the Workstealing scheduler. The overhead of the Workstealing scheduler also increases with more tasks, and it is higher when more workers are used. The overhead of RSDS is about 3 to 4 times smaller than the overhead of Dask, and if we zoom on the RSDS part of the chart, we can see that it has a similar behavior to Dask, where Workstealing has more overhead, although on a very different absolute scale than Dask. If instead we fix the number of tasks, in this case it's 25,000, but increase the number of workers, we can again see that the overhead of Workstealing in Dask keeps increasing, while the overhead of the random scheduler stays constant. RSDS again has several times smaller overhead than Dask, and if we zoom on it, we see a similar pattern where the Workstealing overhead increases with each added worker. Now that we know that RSDS has a lower overhead per each task than Dask, we can return to the worker configuration example from the beginning of the talk. We have seen that using a worker process per core did not provide ideal performance with Dask. However, thanks to its improved runtime efficiency, RSDS is able to use a single worker per each core and thus achieve the best performance out of the box. We can also see here that if we only have a single worker per node, the GALE limits utilization so much that even the reduced server overhead doesn't help. And finally, in this chart we show that RSDS can scale to a higher worker count than Dask. Although, for certain workloads, there is still a tipping point from which on RSDS gets slower with each added worker. Therefore, in future work, we would like to further increase the scaling potential of RSDS. For example, the overhead of the Dask worker could also be reduced, and part of the scheduling could be moved to it to reduce stress on the centralized server. We have also found some use cases where the bottleneck lies not in the server but in the client when it creates too large task graphs. We could therefore try to avoid materializing large task graphs on the client, for example by sending only a symbolic description of the task graph to the server. We also suspect that it could be worthwhile to optimize for specialized workflows, for example by leveraging MPI or InfiniBand collective operations for performing Dataframe aggregations. In conclusion, we have shown that for certain workloads, investing time into implementing a clever scheduler might not help much if the runtime efficiency of the centralized server is low. We have also presented RSDS, an open-source Dask server alternative that has a swappable scheduler, scales to a larger number of workers than Dask in common workflows, and it is compatible with unmodified Dask programs. You can find RSDS on GitHub at the displayed link. This is the end of the presentation. Thank you for your attention. I am now open to questions.